Okay, so now we have Yasmin from Zandia. She's going to share. Oh, Argonne. Sorry, wrong national lab. She's going to share our experience porting LAMMPS to Aurora.
Hello, everyone, and thank you for having me here today. Okay, I guess I have to stick here. I apologize for my voice. I can confirm that I have no sickness. I got tested yesterday. So the project that I'm going to talk about, which I'm happy that it was right after AMBER, it is again another molecular dynamics simulation package. So it's an application study. This project was part of a, okay, so is the arrow key working? Okay, this was part of the ECP project. You guys may have heard of it or not. So this was a big Department of Energy, multiple billion-dollar project over 6-7 years. And the goal was to make applications ready to run on the exascale machines across the DOE national labs. So there was lots of projects, and this work that I'm presenting today was part of that project. So it's called EXALT. So the focus of the EXALT project had multiple components, but the one that I will talk today was about LAMMPS, which is the MD simulation package, and I will give you a quick intro of what it is. And they wanted to run millions of small MD simulation replicas via ParseSplice, which is like just kind of generate a bunch of snapshots on as fast as possible. So their target, and don't worry about KPP, their target was related to one specific function that we are calling a SNAP, and you're going to hear toward the talk, which is stand for spectral neighbor analysis potential. So within within MD simulations, basically what happens is you want to create a understanding of the physical, chemical properties of your system, and you use Newtonian's equations of motion to understand the environment around your particles, atoms, or whatever you want to call it. Now, to define those, we are not explicitly define electrons, so we use what is called force flow, which is an equation. So it's a mathematical description. So this is what a SNAP is exactly for. So it's a total energy is composed of sum of energies of individual atoms, and I have a little bit of equations here, and then potential energy is a sum of weighted by spectrum components. Now, you don't need to worry about what they means. What you need to know is this is a very complex sort of defining a function. So it's not the regular MD simulations that you may see. And in this particular case, what they did, they replaced the Gaussian approximation with a linear regression. So they were like more robust, faster, and straightforward for analysis, which I'm not going to get into anymore. Now, today, let's say, and the work that I'm going to present is mostly done on Aurora. So today, if you want to, let's say you want to run LAMMPS, you can easily just go grab from the GitHub repository, download it, and just go to the source directory and do makefile, just simple command. So it works just fine. Obviously, this was not the case when we started, but today this is how it is. Now, the work that I'm talking about is the optimization of a specific potential. And for LAMMPS, so right now we had AMBER that they were talking about, like every code they have to port it to a different language model for different machines. LAMMPS is basically using two ways of accelerating. So one is KOKKOS and one is like GPU, so CUDA, HIP, OpenCL, and so on. The KOKKOS is an abstraction layer that you may heard of it. And I think there will be a talk from Daniel Art tomorrow about it. So it allows you to port your code with as many backend as you want, as many different architectures as you want, but you don't have to change your code. So it's just you add that on the top of your code, and then you can simply like use different architecture. So that's kind of makes it easy, but it also makes it complex because you have another layer on top of your code. So now I am like gonna go jump like sort of back in a couple of years ago and show you where we started and where everything is standard and like how it is today. So these plots on here shows you the performance of a SNAP potential, specifically a SNAP potentials on different architectures at like 2021. And the higher means better. So as you can see, like the A100 is doing very well, and then V100 and MI100. And then you can see PVC is just literally one dot. So it was very low. And then in the other side, we just kind of zoom in to see where everything stands. So that's where we started. Okay, if I can get this thing to work. Oops. Okay. So now this table basically shows you the figure of merit, which is what we use to define the performance. So in this case, it's the formula that I defined was the steps times atoms divided by the time to solution. So what you want to look at is the Polaris, which is A100 GPUs. And to be an equal sort of comparison, you want to do one GPU of Polaris, and this is a single node, to 2 tiles, or today is called a stack of Aurora GPUs. So in Q3, so Q3 of 2023, you can see that it's significantly lower than A100 GPU. But at the end of 2024, you can see it's basically higher than, and the higher means better. So we just got there. And in this plot in the top, you can see how over time we were able to improve. So there was like some time that nothing was happening, and then we had a jump and then another jump. So basically the developer, I guess, life. So today we have the snap on Aurora PVC with 2 tiles that is faster than A100, and that took us a while. So we were at 75%, and then to get over that, that took a lot of different optimization that I will talk in a bit. And you can see it's and I'm not showing it here, but it's also competitive with MI250X. So we also did some other testing. So I am not really getting into the size of the system, but the size was the one that it was set for the ECP, specifically ECP project, which has 20,000 particles for a type of, so it was the largest sort of equation that they could use. So that means they had more coefficients or more complex. And as you increase the number of particles, we see that the form did increase a little bit on PVC and also on A100. But that's just like sort of us kind of looking at it, see what's happening. And then there's just a note about CPU that today is faster than it was yesterday. Oops. Okay. So this plot shows the single node snap performance on multiple different architectures today. And you can see the one that is higher means better, and like the optimized version, which is what we have today, is highest than all of the above all the other architectures. Now, this optimized version, we did test it on Polaris and Frontier, and we didn't really see a significant change. So the optimization was mostly helpful for the Aurora architecture rather than other architectures. Oh, God. Oh, this is not, okay. And this one shows you that today you can actually run on more than 1,000 nodes of Aurora. So this is a weak scaling of LAMMPS with a snap. So LAMMPS historically had a very good weak scaling. This potential was kind of complex, and we were hoping to see that. And you can see that it is good. This is all obviously earlier studies, and today we don't have access right now, but this is earlier studies of that, but you can see it's a good weak scaling. Now, what if you're gonna change system and you do like a different system, which is what this plot is showing you. So here I tried with the different types of system, more realistic for the scientists that they will wanna do their analysis with. And you can see compared to Aurora and Polaris and the ideal weights, they're basically matching. And the scaling is perfect. Now, there is this one that is on the 2 nodes that you may see, oh, what is this? This is just basically user error. And I didn't have enough time to fix it, but when I tested it on SolidSpot, this was perfectly good. So this is a higher number of particles per system, which is more realistic. So it shows that even if you're adding more work to the GPU, you're still kind of seeing the same observation that you did with the smaller load, which is what we would like to see. Now, if I want to go back in and say what we did in the snap to make it to where it is today, so we looked at the bottleneck kernels, and there's multiple of them. The ones that I'm calling them, there are 3 ones that we focus on: the compute UI, fuse, and compute UI. Okay, and this one shows you the time to solution for different kernels when we sort of started the studying, and then the SGI said it refers to subgroup size and 16 and 32. So one thing that we learned through our studies was different kernels liked different types of subgroup size, which was one of the optimization we did, but it have to be specific to the kernel. So it wasn't like all like the same thing. But our goal was to match the A100, and you can see we're not there yet. And here I'm showing to you a step-by-step what happened. So the kernels were like 1.5 or to 4 times slower on one tile of PVC compared to one A100. Compute YI and then ZI, which is basically compute YI, I mean additional extra calculations, they were the major bottleneck. So that's the one we started focusing on. And then when we look at it deeply, and we notice that the 4D KOKKOS view is one of the places that is actually taking a lot of time, and is related to basically the integer operation that adds to the overhead. So we're like, okay. And then through this process, we use a lot of tools with help of Intel and also Argonne experts. So VTune, Math, we have to like kind of stare at these tools, kind of look at them and understand what's happening there. So this is just showing you a snapshot of, okay, there's relative number of integers are still like kind of high, but what is happening? And we thought, okay, I think it still is the KOKKOS for DBU. And this is another tool that we use. Okay, so what happened? We said, okay, what if instead of allowing the KOKKOS and also the code by itself does these operations, we do it ourselves. So we do a direct pointer to these operations and then pre-compute the part of the 4D index to make it basically simple and then don't touch the rest of them. Would that help? The answer was yes, it does help. And you can see here from the 2 tiles to 1 tile, so the middle two, you want to compare them, you can see the numbers are getting very close, but it's still we're lower than the A100 with the CUDA. So what did we do more? So this is what we are today, the blue number at the very end. Basically, we did multiple different things. One thing is you guys probably know already that the KOKKOS we have, in the SYCL we have different types of pointers for addresses, the global and local. Now, a snap uses KOKKOS level 0 scratch memory or shared memory, which is the local address space. But KOKKOS always returns it to the global address space. And that was an issue because it added overhead to our calculation. So there was like 2 sort of approaches or workaround that Mike and Brown from Intel, he basically said, okay, let's just cast the shared memory pointers directly from the global to local address space. Daniel Art, who is here today, and he has created a bunch of different experimental KOKKOS interfaces that is available for you to grab it from GitHub, which I definitely suggest you to do though. Also did basically created a version or a Get version that basically uses the scratch memory inside kernels that allows the user to specify the scratch level at the compile time. So this was not something that it was doable at the time. And then another step that it was done was, okay, we talked about work group sizes, that every kernel had its own sort of preferences versus 1632 or so on. And this was not something we could do it at the time. So again, Daniel from who's the KOKKOS developer help us to kind of implement that within KOKKOS so we can identify those. And then also another issue was basically high register count that causes register spilling. So we had this basically using large register file within our sort of a snap file that also helped with optimization. So all of these together was basically what we have today, which is 1.4x faster than A100. And within, like, if you look at the tools, for example, Math, which is the memory tool, it tells you the cache utilization for the, for I'm not gonna like ULIS total, which is one of the way that stores the arrays, increased from 30% to 117%. And basically casting the shared memory pointers from global to local basically help with reducing the additional control flow. So this is another way of like me looking at the VTune and say, okay, this was like a top level shows you like the 33% of usage, and then it comes back at 24%. And then, so basically the ideal time is you want a lower number, so the lower is better. So with that, I just want to say, okay, so I'm going too fast. So further optimization of 4D index calculation was like one of the main things that we did to help with this optimization. Manually casting shared memory pointers from global to local address spaces, reduce the additional control flow due to the generic address space operations. And then there is experimental KOKKOS interfaces added to specify scratch level at compile time. This is available at GitHub. And then the same effect was impacted with the manually casting pointers. The work group size was another thing that we did. And also one thing that I didn't mention here was like fusing all these 3 fuse kernels. So there was like in a different dimension, X, Y, and Z. Now it's all together. Excuse me. So our future direction is basically to continue pushing the performance optimization of a snap. One thing I want to mention that this optimization, besides the KOKKOS, is actually not public yet. So that's one thing we're working together right now with Intel. and our developers, other developers, to make sure that we can push it back all LAMMPS. So the goal is like everything will become available to LAMMPS. So you just grab it from the GitHub LAMMPS and you can do it. One thing I want to mention is that having KOKKOS is basically enable you to run on any architecture. So that's a good thing, but that adds a level of complexity to it. I would like to thank everyone here, especially Renzo, Chris Knight, Varsha, Daniel Art, who is here, Stan Moore, Mike Brown. And also we had a lot of discussions with WeTune and other compilers and runtime people. Zinmintian, I think I saw his posters here. So there was a lot of, this was a very much developer kind of discussions constantly, like you need help with them, especially because it's on Aurora and it's like a sort of as we go, things changes. With that, this is acknowledgement I have to have. Thank you all for your attention. I can address questions because I went through fast.
So the performance comparisons you showed were the CUDA implementation running on the A100 versus the SYCL implementation running on the.
Yes.
Did you do a compilation of your SYCL code with a NVIDIA backend and run it on the A100?
I did, and I don't have it here, but yes, we did.
Okay.
But that
And
is,
how can you tell us how it was if you don't have the graph, or
it
you want-
is so the SYCL implementation on NVIDIA is lower in performance compared to the SYCL implementation on Aurora, if that's what you're asking.
compared to the native CUDA implementation?
This is still lower. So I compare it to the max. So the CUDA implementation is highest in terms of performance compared to other implementation. And I think that's related because of the software availability that we have on Polaris, which was done, this was done, the NVIDIA with the CUDA backend was done on Polaris. So that's related to that more than like the actual software.
Hi, thanks for the presentation. So this is a very specific kernel. Any plans to port any other kernels? I mean, LAMMPS has a lot of, different potentials implemented.
Yes, so LAMMPS has a lot of potentials implemented, and basically what we've been working on by using this kernel as sort of a benchmark is to make sure that the KOKKOS with the SYCL backend is mature enough that we can port a lot of other ones to it. So as a facility, that's part of our goal, to make sure as many I guess force fields are available for users to use that. So the answer is yes. How many are there? I don't know yet.
So do I understand correctly, anything that KOKKOS is, so, a lot of things I think in LAMMPS are using KOKKOS, right?
Yes.
So everything should then work out of the box, or?
So today, if you want to install, so I guess there are two different ways for KOKKOS. So you can have a KOKKOS that comes with the LAMMPS and just use that as a package. So get the LAMMPS GitHub repository, install it, run it. It will be functional. It will be correct. Not optimization, I don't know. You can also get the developed versions of the KOKKOS, and then you just directly give the path to the LAMMPS, and then it still works the same. But then you will have a lot of, like, for example, changes that Daniel made in that, and it's available to you, and it may help your optimization. You don't really have to make so much changes. It's just separate installation. But in terms of like other packages, the goal is to be available for the ones at least they would want to run on GPUs or at least accelerators. That's our goal basically. And I think for Reacts and Snap and some others, there is still work on that too.
Thank you.
Hi, was the code basically just a straight implementation in KOKKOS, or were there cases where you had to do like escape hatches and call and have direct SYCL code as well?
You mean today or from the beginning?
I'm just
So-
like curious the process here and.
The process was actually, we started with the mini application, which was a test snap that it was actually done with the OpenMP target offload, and then major modification done on that part, and then we use that to push it back to LAMMPS. And today it's all KOKKOS. We do have to change some stuff with the SYCL and like underneath, I guess, but it is KOKKOS, yeah.